Welcome to our second video in our Class 20 series of lecture videos. In this video, we'll be talking about ethers and the chemistry of epoxides. How fun! We're already familiar with a few ethers. This is diethyl ether, known by my biology colleagues as fly nap, because it's a nice anesthetic, not only for humans, but for fruit flies. Here we have methyl tert-butyl ether. We've seen some synthetic approaches to this, either SN1 or SN2, starting from simpler starting materials. Here is 4R methoxy 1-pentanol. We still remember our stereochemistry and naming with stereochemistry. We could call the methyl tert-butyl ether also 2-methyl 2-methoxypropane. I'm partial to MTBE actually. Here's tetrahydrofuran, an important polar aprotic solvent. We could call it oxocyclopentane. Of course, tetrahydrofuran begs the question, what is furan? Well, here's furan, but if you add 4 hydrogens, it becomes tetrahydrofuran. Here's oxocyclopropane. Somehow we cut off the E. It's an epoxide, otherwise known by the common name ethylene oxide. So let's review common ether syntheses. Here we've got 1-bromopropane. If you add in sodium methoxide, we primarily favor SN2. We might get a little E2 byproduct, but in the SN2 paradigm, we get methylpropyl ether plus sodium bromide. Here is tert-butyl alcohol. If we add NaH, we lose hydrogen gas. We form sodium tert-butoxide. If we then throw in methyl iodide, we get MTBE through an SN2 reaction. And of course, we get a little sodium iodide. Here we have our tert-butyl alcohol. If we add in H2SO4, a little catalytic acid, plus an ocean of methanol, then we'll form MTBE through an SN1 reaction as our major product. That's nice. What else do we have in this particular lecture video? Well, let's recall intramolecular SN2 reactions. If we have a molecule that has both a hydroxyl group and a good leaving group, we could hit it with sodium hydride, lose hydrogen gas, create a sodium alkoxide, which would then do an intramolecular SN2 reaction. Here we formed oxocyclohexane and sodium bromide. Here we've got a molecule that has a hydroxyl group and a chlorine, primary carbon that it's bonded to. We add sodium hydroxide. We do proton transfer first. So we create sodium alkoxide, which then does an intramolecular SN2 to give us our oxocyclopentane and sodium chloride. So recall, acid-base reactions are always faster than SN1, SN2, or E1, E2 reactions. Intramolecular reactions are faster than intermolecular reactions in general, unless we've got a ring that does not have a very high rate constant for formation. Here we're forming a 3-membered ring. That's a very fast process. If we added sodium hydroxide to this 2-bromoethanol, we would deprotonate it, and we'd do an intramolecular SN2 reaction and form our ethylene oxide. For larger than 6-membered ring sizes, competing intermolecular reactions occur. For example, if we were to try to form the 7-membered ring, it would be slow. Even though it's an intramolecular reaction, we could have, an intermolecular reaction byproduct, which would be one of these reacting with another one of them to give us this product. How do we fix that? Well, I think we discussed in that particular series of notes that we could do the reaction under high dilution, so lots of solvent to slow down the intermolecular reaction, because SN2 in an intermolecular sense, it's a bimolecular reaction. It depends on the concentrations of the nucleophile and the electrophile, so we slow down the intermolecular process. We could think about forming epoxides on cycloalkanes. If we have the hydroxyl group and our leaving group cis, it's a slow process. It's kind of stuck. It can't do SN2. Why? Because SN2 prefers a backside attack. It would be difficult for this oxygen nucleophile to reach around on the backside to kick out this leaving group. However, if it's a trans orientation on that cycloalkane, we can in fact do the SN2 quite easily. That sodium alkoxide would come from the back side and kick out the bromide leaving group, and we'd form this nice epoxide. So I think all the material above this point, this line drawn in the notes, will go on our first midterm. I think this is probably a good point to end this particular video. So good luck on the question, and we'll see you in the next video.